Okay, we are back. Lesson 10.3, composite functions. Composite function, let's do some definitions. The composite functions are functions that are formed from two functions, f of x and g of x, in which the output or result of one of the functions is used as the input for the other function. The composition of f of x and g of x is defined as f of g of x. So see how g of x is nested inside the f of x function, and is formed when the equation of g of x is substituted into the equation of f of x. F of g of x exists only for those x in the domain of g for which g of x is in the domain of f. F of g of x is read as f of g of x, or f at g of x, or f composed with g. My preference, I will use this reading of it, f of g of x. Another way to write it is f of g of x is another way to write f of g of x. So it's this little open circle thing. Okay. Composition functions of functions must not be confused with multiplication. That is, f of g of x. So a little open circle does not mean f times g of x, which is the product, right? So do not get those two confused, okay? Remember, composition functions have that open circle. Order matters. F of g of x is not necessarily the same as g of f of x. F of g of x means first substitute into g, then substitute the result into f. G of x is the reverse, means first substitute into f, and then substitute the result into g. Let's do our first example. Evaluate a composite function. F of x equals the absolute value of x, and g of x equals x plus 1. Determine first f of g of negative 11 and g of f of negative 11, and let's use two methods. Method 1, determine the value of the inner function, then substitute. So the inner function, I'll call this a, I'll call this b. Okay, for a, the inner function is g of negative 11, and that is negative 11 plus 1. So g of negative 11 equals negative 10. And then we do f of g of negative 11, okay, which is 10. So I'm substituting in f of negative 10, and that equals the absolute value of negative 10. So f of negative 10 equals 10. Part B, I need to find the inner function first, f of negative 11, and that equals absolute value of negative 11. So f of negative 11 equals 11. So g of f of negative 11, I'm going to substitute in 11, g of 11, and that equals 11 plus 1. So g of 11 equals 12. Okay, let's remember those numbers because we'll use part B. Let's determine the composite function first and then substitute. So let's compose the two functions. F of g of x. So I take g of x, which is x plus 1, and I substitute it into f of x. So that equals absolute value of x plus 1. Okay, and then f of g of negative 11. So anywhere you see an x, I'm going to put a negative 11 plus 1. Oh, what am I doing here? Sorry. Negative 11 plus 1 absolute value. And then that's absolute value of negative 10, and that is 10. So we get the same answer as we do in the previous example. Part B, let's compose g of f of x. And when we do that, I'm going to substitute f of x, which is the absolute value of x, into g of x. So I get this, absolute value of x plus 1. So g of f of negative 11 equals negative 11, absolute value of negative 11 plus 1. So that is 11 plus 1, and I get 12, and that is in fact the same as before. Okay, so two different ways to do this. Example 2, let's compose some functions with restrictions. Okay, so when we're dealing with square roots, you might remember from radicals, there are restrictions for the radicand, so what's under the radical sign. Given the function f of x equals square root of x minus 1 and g of x equals negative x squared, determine g of f of x, then state the domain of f of x, g of x, and g of f of x. Okay, so let's compose. I'm going to do okay, so I'm going to substitute. So this is like saying g of f of x. I'm going to substitute f of x into g of x. Okay, so when I do that, I get negative square root of x minus 1 squared. So g of f of x equals negative x minus 1 . Okay, and then let's see. Then state the domain of f of x, g. Let's state the domain of all three. So f of x equals square root of x minus 1. Okay, remember we set the radicand equal to 0. Oops, we say it's greater than or equal to 0, and then we solve, and the restriction is x must be greater than or equal to 1. So the domain here for this one, domain is x such that x is greater than or equal to 1. Okay, or in interval, that's set notation. Let's do interval notation, or so the left boundary has to be greater than or equal to 1, so square bracket with the left boundary, then positive infinity. Next one, g of x equals negative x squared. The domain is, this is all real numbers for x. So we're thinking about a downward facing parabola, or in interval notation, there you go. Okay, the composite function, g of f of x, that equals, so we can't forget about the radical sign. This one will have the same domain as before, because of the restriction of square roots. Okay. Next page. Okay, example 3. Determine the composition of two functions. Let's see. We have f of x equals x plus 1 and g of x equals x. Determine the equations of y equals f of g of x and y equals g of f of x. So let's do this example. Okay. You can use either method. Let's see. Actually, for the equations, so we'll have to do this. Y equals f of g of x. Okay, I'm going to substitute. So f of g of x equals, I'm going to substitute g of x into f of x. So I have x squared plus 1, and that's just x squared plus 1. Okay, and then we're doing g of f of x, so I'm substituting f of x into g of x, so f of x is x plus 1. So I'm going to substitute x plus 1 into g of x. I have x plus 1 squared, and my resulting function is x squared plus 2x plus 1. State the domain and range of each composite function. So my domain is all real numbers for x, and my range is y is greater than or equal to 1 for all real numbers. Let's practice our interval notation. So this is greater than or equal to 1, so it's a square bracket 1 and then positive infinity round bracket. Okay, that's the first part. Second part, g of f of x equals x squared plus 2x plus 1. Okay, our domain is, again, all real numbers, and our range is this one. If you graph this on your calculator, it will have a vertex at y equals 0. So y such that y is greater than or equal to 0. Okay, and let's not forget interval notation and interval notation. Okay. Letter C, determine f of g of 16. So f of g of 16. I'll take my original function, sorry, our composed function, x squared plus 1. And we'll plug in 16. And I get 257. G of f of 3. Take my composed function right here, x squared plus 2x plus 1. And then I'll plug in 3. And I get 16. Okay. Okay, example 4, determine the original function. So we're going to go work backwards from a composition. Okay. Note that g of x is the inner function, f of x is the outer function. Okay, look for a function that may be in common to more than one term in h of x. This will help determine the inner function. Okay, so if g of x, if we're defining that g of x is the inner function, well, I see x plus 5 and x plus 5, so g of x must, if we think backwards, it must have been the function that we substitute into f of x to make h of x. Okay, so g of x must be this function that's substituted. Okay, so if we think about it this way, h of x equals g of x to the 5th minus g of x minus 2. So this is what we're thinking about with substitution. So f of x, the original function that we took g of x and substituted into, must be in the form x squared minus x minus 2. Okay. Again, look for that common term. Okay, what about here? I see a common term of cube root of x. Okay, so I'm thinking right away the inner function g of x is cube root of x because we see it repeated. So if I rewrite h of x in terms of g of x, this is what it looks like. Okay, so if that's what h of x looks like when it's composed, what does f of x look like before it gets composed? Okay, so that must be x. Okay. Next page. Function composition with 3 functions. So you can compose 3 functions, 2 functions, 4 functions, however many. So given the functions f of x, g of x, m of x, and n of x, determine each composite function, state the domain of the composite function, and sketch its graph. Okay. All right. H of x equals g of m of n of x. So the way I like to think about this is this part. Let's rewrite it like this. Okay. All nested like this. Okay. So the first thing I'll do is I'll figure out what is first thing I'll do is I'll figure out what is m of n of x. So I'll take n of x and I'll substitute it into m of x. So if I take n of x and I'll substitute it into m of x, which is just absolute value of x. So n of x goes into absolute value of x. I get m of n of x equals absolute value of x plus 2. Okay. So now that we found this inner function, let's do g of m of n of x. So g of x equals 1 over x. And wherever this x is, I'm going to substitute in this x plus absolute value of x plus 2. So g of m of n of x equals 1 over absolute value of x plus 2. Okay, so here's our composite function with 3 functions composed. Let's see, what do they want? State the domain. So the domain of this composite function is x such that x does not equal negative 2. Okay, and then let's graph this. So when we graph it, non-permissible value at negative 2. So I'm just going to sketch in my asymptote here. Okay, and then our negative 3, 1, right about there, and it's going to look something like this. I'm going to have a horizontal asymptote at y equals 0, and then right about there, and then I'll just sketch that in, and again, horizontal asymptote. Okay, let's try another one. Letter B, h of x equals n of f of n of x. So n of f of n of x. Okay, so first we'll do the inner part, so f of n of x. N of x equals x plus 2. F of x equals square root of x. So I'm going to take n of x and substitute it into f of n of x. Okay, so f of n of x equals square root of x plus 2. Okay, n of x equals x plus 2. So we're going to substitute it back into the innermost part. So n of f of n of x. So I'm going to substitute this into the x. So I get n of f of n of x equals square root of x plus 2 plus 2. Domain here is, so on this part I need that x plus 2 to be greater than or equal to 0, so x must be greater than or equal to negative 2, so that's going to be your domain, x such that x is greater than or equal to negative 2. X is an element of all real numbers. Okay, and let's graph this off to the side here. I have just a couple tick marks here. So negative 2, 2, I have a point. Negative 1, 3, I have a point. And then 2, 4, I have a point. Okay, so it's going to look something like this. There we go. Okay, next one, example 6, composite functions and inverses. Two functions are inverses if the inverse of x composed with f of x. So the inverse of f of x equals x. So we'll show you what this means. Determine the functions are inverses of each other. Okay, so we have to compose each of the functions. Okay, so the inverse of f of x equals, so in f of x, so in the inverse of f of x, I'm going to substitute f of x. So 3x minus 2 plus 2/3. Let's simplify that. I get x minus 2/3 plus 2/3. I get x. Okay, so we meet this condition where if we compose the function with each other and we end up getting just x, so since the composition of f inverse of f with f of x equals x, the functions are inverses of each other. Okay, letter B. Let's do the same thing here. Let's try inverse of f of x equals, so we take f of x and we plug it into the x value for inverse of x. So 1 minus x minus 1. And what do we get? 1 minus x plus 1. I get negative x plus 2. So let's make a statement. Since the inverse of f of x does not equal x, the functions are not inverses of each other. Okay. We just scratched the surface of inverses. In the next two lessons, we'll go way more in deep onto what inverses are all about. But for now, this is a good exercise in using our idea of composite functions to prove whether two functions are inverses of another. Okay, just keep that in mind. We'll come back to it in the next couple lessons. Okay, last page, we're going to do an application. Example 7. The price of 1 liter of gasoline is $1 and $1.195 dollars. On a level road, Chloe's car uses 0.09 liters of fuel for every kilometer driven. So this will be a composite function problem. Let's see what happens. If Chloe drives 50 kilometers, determine how much the gas costs to fuel the trip. State how many steps it takes to solve this problem without composition. So we know that Chloe's car uses 0.09 liters of fuel for every kilometer driven. So volume as a function of distance driven is stated as 0.09 d. So this is fuel consumption as a function of distance. driven. If Chloe drives 50 kilometers, determine how much the gas costs to fuel the trip. So 50 kilometers, so V of 50. What volume of gas did Chloe use? So Chloe used 4.5 liters of fuel. Okay, so that's one step. It's going to take one more step to determine how much the gas costs. This is the volume. Okay, I need cost, dollars. So we know that the price of gasoline, okay, the price of gasoline of 1 liter of gasoline is 1.195. So let me write this function. So part 2, m of v, m as a function of v equals 1.195 times v. So this is price of gasoline as a function of volume. Okay, so m of 4.5, that will get you your cost, because we know we use 4.5 liters of gasoline. So what's the total cost of the trip for fuel? That's $5.38. Okay, so that's 2 steps. How many steps? 2. B, state a function v of d for the volume of gas consumed as a function of the distance driven. V of d equals 0.0, v of d equals 0.09 d. State the function m of v for the cost of the trip as a function of the gas volume. M of v equals 1.195 v. Using function composition, combine the functions from parts b and c into a single function m of d, where m is the money required for the trip. Sketch the graph. Okay, so we are looking at m of v of d. Let's compose those two functions. So you take v of d, and then we substitute it into anywhere we see the v. So we're going to substitute right into that v. Okay, so m of v of d will equal 1.195 times 0.09 d. Okay, I'm going to shorten this to m of d because now it's the cost of gasoline as a function of the distance driven. So we get 0.10755 d. So m of d equals 0.10755 d. Let's sketch the graph. So it's going to look linear, something like this. Okay, not quite on the line there, but you get the idea. Okay. Letter E, solve the problem from part A again, but this time use the function derived in part D. So with the composed function m of d, 0.10755 d, I'm going to substitute in a distance driven of 50 kilometers, and indeed I get $5.40. How many steps? 1 step. Explain how function composition is useful for the problem. Faster calculation, fewer steps, so it's less messy, right?